Hello, my name is Henry Segura, and I recently graduated from San Diego State University in mechanical engineering, and I led the charge in the mechanical design for this vehicle. In this video, I will be discussing and demonstrating a couple of unique mechanical features and core objectives for our 2021 AUV Pico. To give a little background, our inspiration for this build was primarily based around our given virtual environment. Back when the school year started, we were faced with the task of teaching new team members the engineering design process, which leads from brainstorming an idea into making design changes suitable for competition. This year's goal was to create a mini sub, a vehicle simple and cost effective for any team member to build, no matter how remote they might be. Although small in size, our goal was to equip this vehicle with the basic components needed to compete in future RoboSub competitions. A notable key feature that makes this build different from our other vehicles is the size and weight. With an average footprint of approximately 15 inches in length and 10 inches wide, with a 3-inch diameter interior, this AUV is our smallest vehicle to date. Fully assembled, this vehicle weighs about 6 pounds, and with its 4 vertical motors and 2 horizontal motors, it is free to move in 6 degrees of freedom. 6 brushless 2300 kV motors with modified underwater propellers is our method of thrust for the system. The main hull is composed of a transparent polycarbonate hull, and along with the polycarbonate window, aluminum flange, some penetrators, standoffs, and fasteners, these are the only off-the-shelf components we used. Everything else was designed and 3D printed in ABS by our team members. Our original design was to use a 3-inch diameter ABS plumbing tube, which can be found in any hardware store, but we used a polycarbonate tube to accommodate for quick testing and better visibility. With our modified 3D printed end cap, this system allows for up to 9 penetrators to access the interior of the mini sub. To best utilize our 3D printed parts, we combined some of the mechanical systems with compliant mechanisms and quick disconnect features to best help achieve our needs. Overall, the total cost of this build is approximately $202 US, not including the electronic components, and $115 US using an ABS plumbing tube instead. With such a small volume given to fit all our basic electronic components, an internal structure was necessary to maximize our space. We organized our internal components to keep the heavier items on the bottom, our connections to the outside near the back, and our wires would be managed with open slots in between each platform. Being a circular tube, it was a challenge to design a structure that would stay in place, so a compressed structure that could attach the sturdier end flange was the solution we came up with. On one end, we would attach our camera mount to a standoff that would house our internal platform and the electronics, and on the other end would be our ESC mounts, which would serve as the back plate for our structure and would include our quick disconnect feature. This whole system was secured to the end flange and would keep all of our components in place. A challenge we faced when designing this vehicle was the lack of pass-throughs available. With 6 motors, each needing their own connections to an ESC, 6 of our pass-throughs would already be used. That left us with a single pass-through for a depth sensor and any additional external payloads that could potentially be used in the future. We came up with a solution to 3D print an end cap box that could be integrated to fit onto our flange. The flat surfaces of this end cap ensures that we have a watertight seal with the flange and penetrators, as well as allow us to move the penetrators to either side if need be. This solved the issue with our pass-throughs, but being that the internal components needed to be secured to the flange, we needed a way to access the interior of the mini sub without disassembling our internal structure. Thus, the team designed a quick release mechanism that could secure to our internal structure in the correct orientation that could still be removed quickly and efficiently. With most of our external components being 3D printed, our creative designs were basically unlimited. For example, our design of the 4 vertical motor mounts were placed near the bottom of the mini sub to allow for complete submersion of our thrusters when placed in the water. Also, the cutout design of each shroud allows for better flow of water when used with reversed or forward thrust, and allows for better orientation of the motor cables as well. A 3-piece motor arm connection allows for modularity
and adjustability on the sub. Subsequently, we would be able to move any pair of motors either forward or backward, according to the changes in our center of gravity due to future additions of external payloads. Each motor ring has an adhesive foam to increase friction and a T-slot alignment extrusion to ensure all of our motor mounts are aligned. A key design theme we want to approach this semester was to use compliant mechanisms in our design. For our vehicle, we attached each motor to a motor arm which incorporates a spring-like compliant mechanism. This was designed to help mitigate any damage to our vehicle in case of a collision. This mechanism would also act as a force dampener, which would help against any initial impacts on our AUV and ultimately help keep our motors and mini sub intact. When tested, each spring arm could deflect around 3 pounds of force. Another compliant mechanism that was used was the autonomous/kill switch. This switch, when deactivated, would detach a magnet from the sensor on the other side of the end cap and would turn off the system completely. By using a bistable compliant mechanism, we can push or lift the arm to one of two positions, activating or deactivating the mini subsystem. Compliant mechanisms can be found all around nature, and the uses for them in engineering are practically limitless. And the team and I will definitely find different ways to incorporate them into future builds. The selection of our motors was one of the biggest factors we took into consideration when designing this build. Adapting brushless motors, normally used for FPV drones, for underwater applications was definitely a big leap, but necessary for our mini sub. Therefore, we developed a motor test bench. This test bench incorporated a motor stand on a pivot, a tank of water, and a strain gauge. Using this setup, we could test the forward and reverse thrust by simply changing the direction of the motors we're facing. By determining the thrust generated with each motor and propeller configuration, we could accurately depict how much power each motor should output and thus making our system more efficient.